Okay.
Yes.
Okay, here we go. Let's put cell phones, other distractions away.
Let's go, Carter Jackson.
Okay, so last unit we learned about the 3 different types of bonding, right? There's ionic, covalent, and metallic. In this unit, we are going to learn how to name ionics and covalents. Metallic bonds kind of just all have special names. They're all of our different types of alloys. So they don't have rules for naming. Someone gave them a name, like brass. What's another alloy? Steel is an alloy. So they just have special names, and you just kind of have to memorize that brass is copper and zinc. And we're not about memorizing in this class because you can Google it. So we're not going to learn metallic bonding. But for ionic and covalent, there's a very systematic way in which you name them. Today and next time we'll be focused on ionic. And then the time after that we'll learn covalent. And then later on in the year we'll learn about this special group called acids. So that will come later. Okay, this is not matching the first page, is it? No. That's awkward.
This skips to I think the next
Yeah, skip to
page.
the next page.
That's where it lines up, huh? Like on the back side.
Okay.
Sorry for the delay. Okay, here we go. Okay, so some general things that we'll see as we talk about nomenclature. First off, we've talked about this before, but an element is only a single symbol. So when I call something an element, it's just Na, or it's just oxygen. On the other side, if it's a compound, that means you're going to have more than one symbol, which means there are more than one capital letter. So this unit is extremely important that you distinguish between capital letters and lowercase letters. Because in chemistry, this and this are not the same thing. This is a single element because it's one capital letter, it's cobalt. This would mean it's 2 elements, carbon and oxygen, so this would be a compound. So you've got to make sure if you are a kind of all caps writer, you've got to change that a little bit with chemistry. The other thing is a formula for, or the name of a compound is always 2 words long. You can kind of think of it as it always has a first name and a last name. Elements are just single words. There's no two-word element. They're all just single. Now, this is just review. I don't think it's on there, but just kind of reviewing the different types of bonds. So ionic is the one where we're transferring between two things. Okay? The way the periodic table is organized, sorry, this is jumping around. I don't know what's going on here. That's okay. We'll figure it out. This blank is right under that big table. We'll go back and fill in those ones we're missing. Okay? We've talked about how the table is organized so that similar elements are grouped together. Can anyone remember what was another name we used to call a column? What's another thing we could also call them? Groups, right? Or families. Because we find that there's similarity between them, one of them being the valence electrons. Okay? Now, valence electrons are the reason why atoms bond and form compounds in the first place, right? We talked about how they do it because they all want to achieve what? Stability, right? And the way to become stable for an atom is to have a full outside shell, those full valence shells. So if you want to go up to where it's bolded right there, where it says valence electrons are the outermost electrons in an atom. And then in this picture right here, how many valence electrons does this atom have? Just one, right? And that's that next blank right there. So really, we're kind of ignoring all the inner ones, and we're only focused on the outer ones. So when we talk about ionic bonding, the biggest thing we want to look at here is how many electrons does it want or need to achieve that full shell in a give and take type of way. Okay, the similar properties that they have are due to that similar number of valence electrons. As we saw when we did that demo of dropping them in water, right, all that group 1 family kind of behaved in similar ways. They all smoked, some just more extreme than others, right? And then the number of valence electrons can be found by going across the periodic table from left to right, just like what we did on our warm-up. So on that last blank right there, the number of valence electrons increases left to right. Now what I want to write on this periodic table here is the charge that atoms form. Okay, so the valence electrons is how many it has. The charge of an electron is how many does it want to give or how many does it want to take. And this should hopefully feel familiar because we've kind of talked about this before. So once again, there's two ways, let me grab a model here, that an atom can get a full shell. Okay, an atom can get a full shell by adding to complete the shell, or what was the other way it could get a full shell? Sharing, good. And then the other way? Giving away. How does giving away get it a full shell, Jeremy?
Because once you have 0 valence electrons, basically the next shell becomes the most outermost shell.
Perfect. Right, remember atoms are like onions, and if you peel the outside shell off, the inner shell is full. Okay? So, that's kind of what we're looking at here. And the way I think about it is atoms will take the path of least resistance, like majority of things in the world. So if everything, I'm going to write my numbers underneath because I can't reach that high, but if you want to write these above, that might make more sense. So everything in this family has 1 valence electron. So in order to get a full shell, what's the easiest thing for this group to do? It's going to lose one, right? So I'm going to write 2 things. So this group's going to lose an electron. Whoa, forgot the O there. So it's going to lose 1 electron. Now, what's the charge of an electron? Negative. So if you lose something that's negative, what happens to you? become more positive. So this column right here forms +1 charges because they like to give one away. Okay? Same thing continuing the pattern. So this family has 2 valence electrons. So their path of least resistance to get to full is to lose the 2 that they have. So by losing 2 electrons, what does its charge become? +2. Very good. Now, since we don't know this group's valence electrons, you can't predict its charge, right? So carrying on the pattern here, this one has 3 valence electrons. Keep in mind the goal is up to 8. So you gotta think, well, what's easier, to lose 3 or to gain 5? It's gonna be easier to lose 3. By losing 3 electrons, its charge would become +3. Everyone seen the pattern here? Now this next group gets a little interesting. Why does this group get a little interesting? Yeah, it's right in the middle, right? It's at 4. So is it easier to lose 4 or is it easier to gain 4? Now here's where it kind of splits. Okay? What's this yellow diagonal tell us again? Yeah, the metal. Everything on the left of it is a metal, right? And everything on the right is a non-metal. The metals at the bottom of the group can form a positive +4 charge. But because they are also part of this weird group of transition metals, it's not always +4. Sometimes it's +2. The elements at the top of the group, because they're nonmetals and metalloids, end up just not ionically bonding really at all. They only do the shared relationship. So in terms of charge, we're just going to leave this blank. Because it's not totally correct to say plus or minus 4, because it doesn't really ever do -4, and it only sometimes does +4. So we're just going to skip it. No, in terms of a test question, once again, I'm not going to ask you one of those, because there's not a pattern we can follow. Okay, now coming here, this one has 5. So now that I've crossed over the middle line, what are these atoms going to choose to do in an ionic bond? Yeah, they're going to get, right? So these ones are going to have, receive, what would be the right way? Gain, there it is, thank you. Gain 3 electrons. Now if you gain 3 more negative things, you become negatively 3 charge. And then continue the pattern, this will be -2, -1. And then what does that tell me about the noble gas family? They don't ionically bond. They do at times covalently bond because they do share, but they don't ever ionically bond. They don't ever give or take. Questions on that? Okay, for hopefully 3 easy smiley faces, flip your page over and answer practice problems 3, 4, and 5 real quick. Number 38. Give me a pencil drop when you're done. Can you guys believe that we might get snow tomorrow?
Really?
So disgusting.
So weird. Like yesterday was like so nice.
How are we gonna get
I wanna be
snow?
working
It's like 80
hard.
degrees
I
out
know,
there.
like literally we're dropping like 50 degrees overnight.
I love it. You know what? You do you.
Jackson, I'm with you. I want to be wearing scorpions right now, not a t-shirt and shorts. It's November.
I know, you talk down.
Yeah, it's November. It's time for you.
No, it's not.
Like I've always done every year.
But listen, when it's freezing, it won't
Okay, you're gonna get creative here with your hand signals. Okay? So you gotta show me the charge. You gotta first show me plus or minus, and then a number. Okay? Sure. Okay, show me your answer secretively for what is the ion charge of aluminum. Good. If you're showing me a +3, you're correct. Down smiley face.
Bro!
Wait, I don't understand. Okay, wait. Oh yeah, no, that makes sense.
So, just a reminder, everybody, give your attention here. So the way you find a charge is you go to where it's located on the periodic table. You go based off how many valence electrons. Then, is it going to lose or gain to either, in a sense, get to 0 or get to 8? Now, the biggest thing is it feels a little bit backwards, sometimes mathematically, right? Because to get a +3 charge, what is aluminum doing? It's losing electrons, right? But keep in mind, electrons are negative, so that's why you kind of have this inverse relationship. Okay, check your other two. You should have a +2 for strontium and a -3 for phosphorus. You have a smiley face for each of those. Any questions on charges? Doing this, by the way, so that's ICAM 4.1, is can you determine a charge from an element? Any questions? You lost your tracker? Okay, here we go, everybody. Give me your focus back this way. All right, now we are actually going to skip in our notes, but this one was a planned skip.
Yeah.
Flip and go to the next page where it says notes 2. I like to, so we gotta learn the language in both directions. So what we mean by nomenclature is in chemistry, we write things like this. Right? Chemists write in symbols and numbers. But when you talk about these things, chemists don't actually say Na2CO3. They say its name, which is sodium carbonate. What you need to be able to do is speak the language in both directions. Give me attention here. Meaning, if I give you a formula, you should be able to tell me its name. Or if I give you a name, iron 3 chloride, you should be able to translate that into a formula. Today, we're going to learn this to formula. Next time, we'll learn formula to name. Once you learn one way, it's easier to learn the reverse. But we gotta make sure you practice both directions, okay? So what I'm gonna do first is I'm just gonna kind of go through the rules, just so we can get them all down on paper, and then we'll do lots of practice to make sure you understand it, okay? But for now, if you're kind of like not quite understanding the rules, just get them on paper, and then I promise we'll walk through it in a bit, okay? So the rules for ionic is the cation always comes first. Just a reminder, the cation is the positively charged ion. So we always write positive first and then negative, it's just the pattern. Okay, so we always write the cation first. The second one is the anion. Okay. Did I miss something? Do I need to go back?
Yeah, real quick, thank you.
Yeah, you're good. Now, with the language of chemistry, the ending, where did it go? Oh, I have to go to the next one. Of IDE is extremely important. Okay? If something ends in IDE, ide, that means it's referring to the element on the periodic table. So if you see a name that ends in oxide, oxide is just referring to oxygen in a bond. Chloride is chlorine in a bond. Okay, so if it ends in ide, you know, okay, I'm looking at the periodic table. If it doesn't end in ide, it actually comes from a very special group of things known as the polyatomic ions. Is everyone okay if I go to the next slide? Okay, oh, so there it is. These are known as the polyatomic chart. The polyatomic chart is a group of things that exist in bundles. If you flip to the very last page in your notes, you should find a polyatomic chart. Okay? Now, this is not all the polyatomics that exist in the world, because there are lots and lots and lots of them, but they're the most common ones, so they're the ones you'll see in this class.
Are we allowed to have this for like the tests and stuff?
Yes. So you'll get to use this on the test. You don't have to squeeze it onto
I
your
don't even know what it is.
Yeah.
Like, but it's on the test. It's not on my period.
Say that one more time. Yes, it is. So on the periodic tables that are normally on your desk, it's on the back of there as well. Yep. Okay, so we don't have to memorize these. We just come here and use it.
Thanks.
Okay. Now, notice that these end in two mostly endings. They either end in ate or they end in ite. Okay? A very common mistake is to read a name such as carbonate, and then you look at the periodic table and the student goes, I can't find carbonate on the periodic table, because it's not there. Okay? Or vice versa. They'll look for chloride on here. They'll be like, I can't find chloride. Remember, IDE is up there. Eights or ites are down here, minus two exceptions. There is a polyatomic named hydroxide. So that one does end in ide. And there is one called peroxide. But outside of that, ate and ite, look here. Okay?
Even cyanide.
Oh, thank you. There's another one, cyanide as well.
I just sounded like a genius. Just like,
Okay, so if it ends in ate or ite, we find it on the polyatomic chart.
that almost right. Did it right?
Okay, then the final step for writing a formula is we have to balance out their electrons. That's why they're bonding in the first place. Okay, so let's do an example here.
Ow.
Okay, let's grab. Okay, so first step is you take, so this is the name, we're translating it into a formula. First step is to find the symbol that it's referring to. So aluminum symbol is
AL.
very good. Sulfide is referring to just sulfur, so S.
That's a common.
Okay? Now I'm going to show you two ways you can balance out the math. pick whichever makes the most sense to you and use that method, okay? The first method is actually by just how many valence electrons it has, and we kind of did this once before. So how many valence electrons does aluminum have? 3. So draw 3 little dots on aluminum. Now once again, if you don't like this method, then you can do the other one or vice versa. But I would encourage you to write both methods down so you have them as options. Okay, how many valence electrons does sulfur have? 6. Okay, now how I'm gonna write, so, yeah, let's do it this way. So if it has 6, how many more does it want? 2. So I'm gonna do 2 little X's to show like, hey, it needs 2 more. Then you just start matching it up and saying, okay, well if it needs 2 more, we can give it 2. Sulfur's happy, but is aluminum happy? Nope, so we're gonna bring another sulfur to the party. Aluminum can be happy by giving that away. But now what? Okay, so bring another aluminum.
Oh,
Bruh.
God.
Stay tuned. It doesn't go forever, I promise. Hopefully some of you I think are seeing it's gonna end actually pretty quick. Okay, so there. But now, bring another sulfur.
Wait, what is going on?
Okay, then I can see the math behind it too.
So this is the idea of balancing, everybody.
Put together and then it's like,
Bruh.
Is you've got to go back and forth until it's all balanced out. Okay, give me your attention here. Yeah, Sam.
So on the sulfur, do you not draw the 4 other valence electrons?
Technically not, because we're just trying to see what it needs to be balanced. You could if you wanted, like if you wanted to draw the 6 that are there, and then showing like, okay, this one has all 8 and this one has 0. I just like to look at it as, okay, this one wants to give 3, so I'm going to draw them as dots. This one needs 2, and then you just have to make sure everybody balances out. Does that make sense?
Yeah.
Yeah, great question. So your final answer for this would be Al2, because I have 2 aluminums, S3. Yeah.
so basically you're just kind of finding like the common denominator between like the things and then fitting them.
Yes. So this is the, I would say if you're a very visual person, this way works great. And use this method all you need. Okay? Another thing you can do visually if it helps, and I have little versions of this, is I have these little puzzle pieces you can also play with if you find it helpful. Okay, so for example, I have aluminum here. That's giving away 3. I don't have a direct sulfur, but I just need something with a 2 for the, so we're gonna use this one. Okay, so if you see, doesn't work out, so I'm gonna throw another aluminum up there. So 2 ALs, 3 of the others. I have small versions of these little magnets if you are a visual person and want to use them to help you figure things out. And you can use these on the testy then.
Yes.
That's totally fine with me. Yeah, Rachel.
Could you do it like the opposite way, like how aluminum needs like how aluminum needs like 5 and then like you sulfur has 6? Is it ever gonna be like the opposite way?
You could look at it that way. The biggest thing, it just has to be balanced, right? So if you wanted to look at it in reverse, I think it could
Well,
still work.
does it matter?
Like who's giving and who's taking?
Yeah.
Oh, yes.
Okay.
Yeah, it does. Because aluminum would never,
Is it always written like the right way? You
so
should
this
use
one's
it?
always giving, this one's always taking.
Okay.
Yeah. Does that answer your question? I see you're asking now. Okay, now another way, if you don't want to do the visual drawing, okay, is kind of like Rachel pointed out, is you just find the lowest common not factor. Multiple, there we go, of both. Okay, so aluminum comes or has a +3 charge. Sulfur has a -2 charge. In the end, the charges have to equal 0. So in order for them to equal 0, you need the same amount of positives as you do with negatives. So the least common multiple between the two of these two would be 6. So to make it be 6, we need 2 aluminums and 3 sulfurs.
Oh.
So you can just look at the charges and balance it out that way.
Yeah.
Yeah, Jeremy.
Is there a reason you wrote +3 for aluminum and then 2 minus for sulfur, or is that just?
Is it backwards? So this is the way actually chemistry typically write charges, is you actually put the charge behind the number. I sometimes put it in front just because it throws students off, and in this case I did both, which is awkward, so. This is like the most correct way. I don't really care how you do it in this class, but yeah, good observation though. Questions on balancing charges before we do some more? Okay, let's skip down. Oh, we got a few more blanks to fill, and then we'll do another practice problem here. Okay, so overview. Okay, is we write the symbol of the cation first, hence why aluminum came first. Okay, with your charges, there is an important thing to recognize. If the name has one of the elements in the middle of the periodic table who we don't know their charge for, it will always have a Roman numeral in its name. The biggest thing is the Roman numeral is the charge of the atom. You don't even have to look it up, it's telling you right in the name, and I'll show you the example of that in a second. And then the biggest thing is they have to balance out to be 0. However you want to figure that out, either with this, drawing arrows, or doing the math, that's why they bond, is they have to equal 0. And we'll do an example of this, but we'll sometimes use parentheses to show more than one polyatomic ion. Okay, we're going to do 3 examples together, and then I'll have you do 3 on your own for smileys. If you're feeling really confident, you can silently go ahead on your own and try these problems, but I can't have you talking to your neighbors right now while I'm trying to help those that want a few more examples together, okay? Okay, let's do potassium chloride. Okay, first step, find the symbol. Potassium symbol is?
Hey.
Thanks, Michaela. Chloride is good, Cl.
Good job.
Okay, any preference? Do we want to do visual or do you want to do the math way?
Math way.
Math way? Okay, potassium's charges.
Oh wait, yeah. Wait, hang on. Positive.
+1.
Yeah.
Chlorine has a charge of -1. So they're a happy couple, and the name is, or the formula is just KCl. Notice that when you write the final formula, there are no more charges because it's balanced. Just like in math, you don't have to put ones, right? So we don't have to write K1Cl1. And then the other just final note is make sure you write them close together. Otherwise it's weird if you have them far apart, because you got to show that they're bonded together. Yeah, you get it.
Why is it that in the first one, it wasn't equal, but this one, they don't have any charges?
It just depends. Yeah, it just depends on what these end up being. If they're the same charge, it's always just 1 to 1. So, yep, just depends. But you always have to check it to make sure.
Okay.
Good question. Okay, let's do the next one. Magnesium nitrate. Okay, magnesium symbol is
MG.
Mg. Nitrate symbol is Remember, ending of H means to look on your chart.
Oh.
So look on your polyatomic chart
Where are you?
and find a thing called nitrate and write the whole thing out.
N-O.
Your kid.
N-O.
And its charge.
N-O.
Does everyone see nitrate? Help your neighbor out if they don't find it.
There is?
Oh, nitrite and nitrate. That's two different.
Yes, and you all look carefully because there's an I and an H. And they are different things. Okay, to balance out the charges, we have to know magnesium's charge, so find that on the periodic table.
+2.
Okay? Okay, so this has a +2, this has a -1. The charges have to equal 0, so how many of each do you need to make it balanced? Good, so we need 1 magnesium and 2 nitrates. Does everyone understand that? Okay, I'm just gonna draw a second one just so we can see, right? Because we need 2 of those to balance out 1 of those. The way we write that is you write 1 Mg, NO3, 2 outside. Because notice this thing is a set. A common mistake is a lot of people would write Mg, NO6. This doesn't show 2 sets of NO3. Even this doesn't show that. You don't distribute it because we want to show, hey, we have 2 of these things. So that's when you use the parentheses. Questions on the use of parentheses? Okay, let's do one more together. Okay, copper 2 fluoride is its name. Let's write its formula. So copper symbol is Cu. Fluoride is just the element, so Cl. So step 1, write the symbol. Step 2, write the charges. Copper has a charge of?
We don't know.
How do we know that?
Oh, it's a Roman numeral.
Roman numeral tells you the charge.
Does that mean it's positive?
Why?
What would it look like if it was negative?
How do I know it's positive?
Well, how would you tell if it's positive or negative?
Roman numerals
You just
negative
know.
two. Actually, don't know.
One is you could say, well, chlorine we know is negative, right? And 2 negative things aren't going to bond. So that'd be one way to go. How's my thing for that? Other ways?
It's the first element.
The first element is always positive, right? The second one is always negative. So technically, if you had a Roman numeral at the end, it would be telling you the charge of this. You actually won't ever, because all the ones that have various charges are metals. And metals are always positive. So there are never any negative Roman numerals, ever. But great question. Okay, balance it out. So to make it equal, we're going to need 1 Cu and 2 Cl. Questions on the Roman numerals? Okay, here's what we're going to do. You're going to do problems 4, 5, and 6 with your table buddy.
Yeah.
Okay, once you have an answer, raise your hand, and if you're correct, I'll give you the homework to get started on. Okay? Alright, ready, set, go.